Okay, we are now recording, or so it says. Great. Can't have a class without this darn thing recording, because I have to upload this thing as a YouTube segment afterwards. And wouldn't I be screwed?
Yeah, I went back and watched it.
I'd be screwed if I forgot to record. And one time last year I did. So I had to do the whole session over again by myself. Just, it's almost like there was my punishment for having forgotten. I'm going to share screen here. And we'll just take a look at where we were. And you can see this here slide. And that's the first one we ever showed last week. And we talked about condensation and rarefaction of sound of molecules in the air made by a tuning fork. And I showed you this slide as being yet another one. And then we talked about waves of light, and we said sound is not like light. Light can travel through outer space. Sound needs a medium to travel through, such as air, water, or metal. This is light, and we talked about that just being how sound is not. Again, this is just a one little area of visible light within all kinds of radio waves, but nonetheless, this is sound waves. Molecules in the air being squeezed together and separated, and we always draw the up portion showing where the molecules are squeezed together. Hi, Nisha has a guest on the show. Great, good to see you again. Nice to see you again. Great.
Yeah, that's my mom.
Oh, great. Pleased to meet you. Good to see you. I was going to ask who your guest was, so nice that you can join us. All right. And knowing where the molecules separate is where we draw the wave going down. And that's just review from last week. And we said one condensation and one rarefaction equals one wavelength. Okay, and we said that the more wavelengths you have, the higher the frequency. So here is a speaker making sound. You've got a rarefaction, the white area. You've got a condensation, the dark area. A rarefaction, the white area. Condensation, the dark area. And we draw the wave going up and down like this because it's easier to do. Hi, Lizzie. Glad you could join us. Good stuff. There's now 4 of us on. Okay. And now when you're looking at the bottom one, you can see the same speaker, and it's making a higher frequency sound. Follow my cursor. A condensation, rarefaction, condensation, rarefaction. And so we draw that wave, the condensation as the up, the rarefaction as the down. You can see that the bottom wave has more bumps per second than the top wave does. So the bottom wave is a higher frequency. We said all sound waves have 360 degrees, just like a circle does. And a circle has 360 degrees going around it. Do a 360 in the parking lot. Okay, well, a wave has the same thing. Begins at 0 degrees, goes to 90, to 180, to 270, back to 360. And now you're starting over again. The 360 is now 0 again. Here it's showing you closer up. 0 degrees phase, 90 degrees, 180, 270, back to 360. Remember, 1 up is a condensation, 1 down is a rarefaction. And 1 rarefaction and condensation together are 1 wavelength. You can have a sound wave going like this too. It can begin going down as a rarefacted phase and then going to condensation. Doesn't matter. Doesn't mean it's not a nice sound, it's just different. And same with this one here. Okay, you've got 360 degrees. It's 1 wavelength. You started here, and now you've gone all the way through, and now you're right back where you started at the top right. 360 degrees. We showed you 3 different sounds or pairs. We said sound takes place in 3 dimensions. Whoops, 3, Ted, only 3 fingers. 1, 2, 3, 3 dimensions. Intensity, frequency, and time. So the top 2 waves are the same in amplitude, the same height, okay? They're just different in frequency. The one wave here has only 2 bumps, and the one behind it has 4 bumps. Here you're looking at, in the middle, you're looking at two sounds. They're the same in amplitude. They're the same in frequency. They're just slightly out of phase with each other. time is the different one here. And the bottom one is showing you two sounds. They're the same in phase. They're the same in frequency. They're different in intensity. Just showing you the three dimensions again. This slide does the very same thing. Two tones of different amplitude, two tones of different frequency in the middle, and two tones of different phase on the bottom. Just review from last week. Then we got to calculating, excuse me, period. What's the time? And think of your watch. What's the time it takes to complete one cycle, to complete one rarefaction, one condensation? Well, A is the amplitude, period is the length of time. And if you look at the bottom here, you'll have 1 second. So how many bumps were in that 1 second of time? 1. So what's the period? 1 second. Period is 1 over the frequency. Frequency is 1 over the period. In other words, the time it takes to complete one cycle is inversely related to the frequency. The higher the frequency, the shorter the wavelengths. The lower the frequency, the longer the wavelengths. And remember we said last week, low frequency, those long waves, they bend around trees, they go over objects, they bend. Low frequencies have long wavelengths. Short, high frequencies are like the bats would use, spitting out tiny, tiny little high frequencies that bounce. Highs don't bend, they bounce. And they bounce off the bugs in front of the bat. And that's the blind bat can catch bugs in midair because it's using high-pitched sounds like radar. It's letting them bounce off of things, and then it hears them, and it knows where the bug is. So these are the physics, the basics of sound waves. And then we went over calculating a few different things with period and frequency. And here you've got the length of time for one cycle, starting on the left, one condensation, one rarefaction. There's its period. What was the time in seconds? How many pitches, how many waves did you have? And we always said, if a sound is 100 hertz, if you're looking right in the middle of good old page, let's see here, if I can, and I'll just stop sharing for a second. Actually, I think I'll go to reshare again, but anyway, it's just good to see you again. Looking at faces. Good to see everybody. It's always much better when people show up to these sessions. It really is. It just makes me feel like I'm not just talking into a screen of a computer, you know? I'm going to pull up the notes that we did last week. I'm going to share the screen here a second. Here, if I can find you. Here we go. I'll hit share screen again. I have to remember to always do this. I'm going to show you my notes now. And you have this too. I'm just going to work the way down. We covered page 1. We're in the middle of page 2, right where you're getting, can you see what I'm highlighting here? Right there. If a sound is 1 hertz, then its period is 1 second. If a sound is 100 hertz, then its period is 1/100th of a second. Always remember, they are inversely related. As frequency is increased, period is decreased. And we mentioned about what humans can hear. And we can hear sounds down as low as 20 cycles per second or 20 hertz, all the way up to 20,000 hertz. And as we age, we lose our high-pitch hearing. And we lose 20,000, and we lose 15,000, and 10,000, and we start to lose 8,000 and 4,000. And look at where it says here, hearing tests, audiograms. They show human hearing sensitivity from 125, basically that's low C on a piano, all the way up to 8,000 hertz. That's 7 octaves. As you double the frequency, you go up an octave in music. Double 125, you're at 250. That's middle C. Like they do in India. My father can beat your father at checkers. Double middle C, double 250, you're up at 500 hertz. Double 500 hertz, you're at 1,000. Double 1,000, you're at 2 and 4 and 8. Those are the 7 frequencies that we test in a human hearing test. We don't bother with 20 hertz, it's too low. We don't bother with above 8,000 hertz because no useful information is found there anyway. So it doesn't matter that we lose that high-pitch hearing as we go through the decades of life. What does matter is when you start losing 8,000, 6,000, 4,000, you start losing those frequencies. And guess what? Now you're having trouble hearing the high pitches of speech. Now you're having difficulty hearing the letter S, the letters CH, as in church, okay? You can hear this, the word speech, E is loud and low. It's the S and the CH. And that's where people with hearing loss begin to say, why are you young people mumbling? People mumble. Well, the coin has 2 sides. Yes, people do mumble a lot and don't speak clearly. That's true. But the other side of the coin is many people begin to lose their treble hearing and they have difficulty hearing those high pitches of speech. And you can think about it much like like these words: hat, fat, sat, cat, bat, and they all have but it's the that tells you what the word is. We've heard that before. We said that last week. So now let's look at, we move to where we end. Whoa, hold on, horses. May you back up a second. Good grief, where were you at here? I hit too many buttons here. Here you go. Wavelength and frequency. The speed of sound determines the wavelength, and the wavelength is related also to the speed of sound. Okay, so we talked about period, we talked about frequency and period being inversely related. Now it's time to talk turkey about what's the physical length of the wave. How long is it in feet? How long is that sound wave in yards? Okay, and wavelength is also, look at where I'm highlighting here, wavelength is also inversely related to frequency. The higher the frequency, not only is the period of time shorter to have one wavelength, but also the physical length of the wave is shorter. So as frequency increases, wavelength decreases. Wavelength involves the speed of sound. Wavelength is the speed of sound over the frequency, and I drew it. Now I'm going to stop sharing screen here for a second, and I'm going to just highlight or show you exactly what I showed earlier. Wavelength is the speed of sound over the frequency, and I did WL over 1 is equal to 340 over hertz. And you can flip that all the way around. You can also say frequency is the speed of sound over the wavelength. And that's just like, all I'm doing is just flipping fractions around. I may have gone 2 over 1 is equal to 10 over 5, or, you know, what is it? I can't even read my own writing. 2 over 1 is equal to 10, or 5 over 1 is equal to 10 over 2. You know, either way, you're just flipping the numbers around. And that's as tough as it gets in this course. We don't throw calculus at you, and that's not the purpose. You don't need to know that stuff to fit hearing aids on people. We just need to know the basics of sound waves. And so we did say that let's just do an example. How long is a 250 hertz tone? How big is that sucker? How long is that sound wave? Well, you'll say wavelength equals the speed of sound divided by the frequency. Wavelength is 340. You can say 343. Doesn't matter. That's exact. Don't have to. I just rounded off to 340. Is 340 meters per second divided by 250 hertz. And what the Sam Hill would that be? Well, I'll get my calculator and check it out here. I can't. Let's see if I can. Okay, 340 divided by 250. That's going to be 1.36 meters. Now a meter is a yard. Okay, a meter is 39 inches. So that's going to be 1.36 yards long. Well, that's about 4.5 feet. So the lower the frequency, the longer those waves. And you can see where those waves would be able to bend around things now, because one condensation and one rarefaction is a couple of feet long. Good grief. Okay, so now we flip the page to the top of page 3. Now we're going to I'm going to share screen again, and I'm going to go back to the good old notes here. Here we go. Here we go. I want my notes. All right, wavelength, we've covered that. And now we move on to the speed of sound. What's the speed of sound? We know it to be 340 meters per second, right at the top of your page here. Or as you would say in good old USA, 1,130 feet per second. It doesn't matter, just as long as you keep things consistent. Okay? We talked about the speed of light. Look at that. 100 million times the speed of sound in air. 100 million. That's not, you can't even fathom that. Light travels at about 300,000 kilometers per second. In miles, light travels 186,000 miles a second. This is what you need to remember. The speed of sound, 4 times faster in water than it is in air. The speed of sound, 14 times faster in metal. That's why you would listen to the railroad track and put their ear on the railroad track to hear the train coming, because the sound coming through the railroad track is going to be a whole lot faster than the sound of the train through the air. And same with the First Nations people, would put their ears to the ground to listen for the hoof beat of the buffalo. You can tell when those buffalo are coming by the sound through the ground faster than through the sound traveling through the air. Sound always needs a medium or something through which to travel. Look at this part here. This is just meant for the nerds, but I want to explain it to you. The speed of sound is influenced by the density and the elasticity of the medium through which it travels. The density is the mass, okay? The heft of it, the mass of it, the density. And the elasticity has nothing to do with rubber bands. The elasticity is, you can almost think of it as the opposite of an elastic band. It's stiff. How stiff is the object? Okay? And we said yes last week, mass doesn't move very well or doesn't carry high pitches very well. High pitches, high frequencies can't travel through mass very well. High frequencies like to travel through stiffness. Think of a spring sticking out of the wall. I'm going to stop sharing and I want to really have your concentration here, okay? Because we're going to come back to this concept again and again, and it concerns resonance. You know when you have a wine glass at Christmas and you, that's resonance. Or you have a bottle and when you blow into it and you, that's the sound traveling through. That's the object's favorite vibrating frequency. All objects have a favorite vibrating frequency, and when you reach that, you've hit its resonance. And now it's, okay. Resonance is influenced by the mass and the stiffness of the object. If the mass is big, like a locomotive, you can't shake a locomotive very fast. Remember, you're going to have to push with 100 people real hard one direction and then pull real hard in the other direction to just try and move that locomotive back and forth. It doesn't like going, okay? On the other hand, if you have a spring sticking out of a wall, think of a thick spring sticking out of a wall. And if you try and pull on that slowly, but if you stand there and go, easy peasy, Japanesey. Stiffness vibrates with high frequencies. Mass vibrates with low frequencies. Everything has mass and stiffness. All mediums, air, cups, china, locomotives, yourself, your own ears have their own mass and stiffness properties. And we'll get to that in just a bit. But right now, suffice to say, the speed of sound is influenced by the mass or the density and the elasticity. Call that the stiffness, okay? Density is the mass, elasticity is the stiffness. The more dense something is, the slower the sound goes. And you might think, well, that doesn't really make any sense. The more dense something is, look at steel. Isn't steel a lot more dense than air? I mean, I can move my hand through the air, but I can't move my hand through steel. If I hit steel or I hit glass, sorry, that's more dense than air. So how come you said, Ted, that sound goes faster through a railroad track if that's more dense than air? That doesn't make any sense. Well, here's where elasticity comes in. Remember what we said about stiffness? Well, a railroad track is a lot more stiff than air is. So the stiffness of the railroad track, the stiffness of steel, far outweighs the fact that it's more dense. Okay, and that stiffness, that makes the speed of sound go faster. So the more stiff an object is, the faster the sound goes through. The more dense it is, the slower it goes. And even though steel is more dense than air, it's also a way more stiff than air, and the stiffness outweighs the density. If we read together, we'll just read it here in the second paragraph on page 3. But fluids and metals are more dense than air, so why does sound go faster through them? Steel is 6,000 times more dense than air. The speed of sound is inverse to density. But steel is way more elastic than air. Think of elasticity as stiffness, the ability to resist being deformed. And the elasticity of steel, we said, is 1,000,000 times 230,000. I'll stop sharing for a second here, okay? Or I'll share the screen and we'll just look at where I am here, okay? Right here. Whoa, right here. Hang on. Read that part carefully, okay? Whoops, I grayed it out and then I lost it. There it is. But the elasticity of steel is 1,230,000 times greater than that of air. So the greater elasticity far outweighs its greater density. And that's why sound goes way faster through steel. Enough on that. Recall wavelength, frequency, and speed of sound are all related. And now look what I wrote in italics here. Look what it says here. The speed of sound in air now, we are looking at air, has no relation to the frequency. A 2,000 hertz tone will travel the same speed in air as a 1,000 hertz tone. It better, otherwise we'd be on some strange, weird acid trip. Can you imagine low frequency sounds reaching us slower than high frequency sounds? We'd be going, that'd be nuts. In air, all frequencies travel the same speed. Remember that. I'll bet you dollars to donuts it's on your next quiz. Ha! And by the way, BTW, okay? By the way, I think we have a quiz in the Dropbox in Blackboard that's ready for you to write after today's talk. And it'll cover today and last week, the stuff we did. This stuff, Unit 1. Okay, look at this thing, Doppler Effect. Check this out, the Doppler Effect. Now, have you ever, and we all have, you ever listen to I think I'm going to stop sharing here and we'll just kind of close. Here we go. Have you ever stood on the corner and listened to a fire truck or an ambulance go by? Dee-doo, gets lower as it goes away. Or you think of race cars at Indianapolis. How come it goes when it goes away? And how come it goes higher when it comes to you? That's the Doppler effect. The Doppler effect says the speed of sound, 340 meters per second or 1,130 feet per second, okay? But now what's making the sound is coming toward you as well. So now the sound is going 340 meters per second plus the speed of the ambulance. So it's going faster. So those waves are getting bunched together between you and the oncoming ambulance. So the waves are squeezed together and the pitch goes higher. And when it's going away, the speed of sound is 340 minus the speed of the ambulance. So now you've got more wavelengths taking, or fewer longer ones, okay? And that's why an object coming at you, it goes, the Doppler effect. Again, the speed of sound plus the speed of the ambulance coming toward you, so that bunches the waves together. So you've got more bumps, higher frequency, and then when it's past you, speed of sound minus the speed of the ambulance. And so you've got fewer bumps. They're stretched out. That's why. What the heck is a sonic boom? Check this out. I'm going to go down here. Check out what a sonic boom is. See if I got a picture of that puppy. Here you go, breaking the sound barrier. We got another one? Nope, just that one. So now you're looking at breaking the sound barrier, and we've heard of that before. Jets do it, and very fast things break the sound barrier. And what do we mean by that? A sonic boom. So here's your explanation of the Doppler effect. I think I'll share screen again. I got to always remember to do that, otherwise I'll forget completely. I'm going to share the screen, and we'll look at the notes here. Good old, here's your Doppler effect. Occurs below the speed of sound, and it just explains it to you what I just did. And here's sonic boom, breaking the sound barrier. This occurs above the speed of sound. The Doppler effect, Indianapolis, that all occurs below the speed of sound. The sonic boom is when you break the sound barrier. Mach 1, the speed of sound. Mach 2, 2 times the speed of sound. So what is the speed of sound? 346 or 340 meters per second, or 1,130 feet per second, right here, top of the page. All right. How fast is that in miles an hour? About 766 miles an hour, about the speed of a flying jet with a tailwind, but a little bit faster. A jet with a tailwind goes about 600 and some miles an hour, okay? The speed of sound's a little bit faster. So when you get into the Air Force, okay, they're flying jets that go faster than passenger airlines. And these are those F-35s and all of those things. They break the sound barrier. Now, when you look at a sonic boom, let's read what it says in the middle of our page. Okay? As an airplane approaches you at Mach 1, you hear the Doppler effect. The frequency increases. All the sound waves are bunched up, right? All the sound waves are squeezed toward you. And now I'll stop sharing so I can get more expressive here, so you can see my ugly mug again. So you're looking at the plane is moving at the speed of sound, okay? And you're standing here, but the plane is going the speed of sound. So all those waves are squeezed together. All the rarefactions are piled, or I should say all the condensations are piled right up on top of each other. So not only do you have all the waves getting smaller, so the frequency increasing, but they're completely put on top of each other. And the plane has to puncture through that, has to get through it. And once it gets through it, there's a huge vacuum, a huge rarefaction behind the plane. And when the molecules of air fill in that big vacuum behind the plane. That's the sonic boom. Okay, so you'd hear all the waves collect, just all build up on top of each other until finally the plane goes through it, and you've got a big vacuum of air behind the plane, or a big rarefaction, and then all the molecules fill in that area behind the plane, and that's the sonic boom. You want to hear it more in weird terms? How about snapping a towel in the shower room, like I used to do to my little brother? You take the towel and you whoosh. You know why that hurts so much? Because the tip of the towel is breaking the sound barrier. No wonder it smarts when you crack a whip, okay? That is the tip of the whip breaking the sound barrier. So does a snap of a towel hurt against the backside of your thigh? No shit, Sherlock, it does. Okay? Anyway, there was my first cuss word in the session. Okay, we are now working our way down to the bottom of page 3. Sound fields. And you will read with me, and I'll just stay with this for a while. Sound fields. You have a free field. You have sound fields. A free field is just an open area where there's nothing for sound to bounce off. Okay? Just a total free field. A free field hardly even exists. Most of the time, sound occurs while you're standing on the street. Oh, sound's going to bounce off the sidewalk. It's going to bounce off of buildings. Sound in a classroom is going to bounce off the walls. Sound in the kitchen. Okay? Most of the time, a sound field is not a free field. A free field means there's nothing for the sound to bounce off. Very rare. Okay? Only an airplane flying in air would have that. Otherwise, we live in sound fields. So when you're looking at a sound field, reflection occurs when sound bounces from one medium to another. Sound carrying through air bounces off the wall. The wall is another medium. The air is one medium. The wall is not air. Reflection occurs. Sound energy in one medium increases because of the added reflected sound off the second medium. Think of a room full of mirrors. You have a candle and you have all these mirrors. The light's going to reflect off of the mirrors. Okay, it's the same thing in a sound field. So you've got added sound taking place because the sound field might be small. And so you've got a lot of bouncing taking place. Reverberation, reflection and reverberation. Think of a sound like a mirror increases light from a lamp, or an actor in an enclosed theater sounds louder than in an open theater because the sound is bouncing off the walls more. Just makes sense, okay? An echo is when the time delay between the original sound and the sound bouncing back, when that time is less than 1/10 of a second, when that is less than is greater than 1.1 second. Hello, hello, hello. You're at the Grand Canyon. Hi, hi, hi. Okay, that's an echo because the sound bouncing back was more than 1/10 of a second. But a reverberation is a really short echo. Think of bouncing a basketball in a gym. Bow, 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 bow. And it's different. That echo is really quick because the walls of a gym are smaller than the cliff sides of the Grand Canyon. Okay? So if I'm yelling at the Grand Canyon, hello, 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 that's an echo. If I bounce a ball in a gym, that's a reverberation. Think of good old Buddy Holly or someone singing it, bebop-a-loo-yah, be my baby, in a gym. You've got that, that's what some people like that in music. It sounds cool, all right? But you don't want it in classrooms. You don't want it with children wearing hearing aids in a classroom. Reverberation is hell on earth for the hearing impaired. What you want to do in a classroom is you want to hang a carpet in the back of the classroom wall so the sound doesn't bounce off the back of the wall. Cheap. School boards never have money. They're probably going to get even less under the present. Anyway, you want to hang a rug on the back of the classroom to absorb the sound and stop the reverberation. You also want to put tennis balls on the bottom of the chair legs so that the chair legs aren't going across the floor. Okay? There's common sense, bless you, there's common sense in reducing sound pollution and reverberation in a classroom. Anyway, just thought I'd tell you that. Top of page 4. Top of page 4, we talk about standing waves. That doesn't mean a wave with legs, okay? It just means a wave that's canceling itself out. I'm going to share screen here, and we'll go to the top of page 4. Come on. Do you think you can handle it, Ted? Yes, you can. Move that little mouse. There you go. Big boy. I knew you could do it. Come on. I think you slide this puppy down. There you go. Okay. Standing wave. A sound bounces back off of a wall, and it's completely in opposite phase with the original sound that hit the wall. So it cancels itself out and creates a dead spot in the room. That's why engineers design theaters, sound engineers. You can't just have a theater just built like that. They have to make them so you don't get standing waves. So the wave bouncing off the wall isn't canceling out the original one, or you'll get dead areas in the room, areas where the sound is really poor. An anechoic room. An anechoic room means the room has no echoes. It is totally reverberation proof. And only rooms that are soundproof have that. If you ever go into a soundproof room, it looks really weird. A soundproof room is scary. You're sitting in a soundproof room, you can hear your lunch digesting. You will hear your ears ringing. You will hear yourself swallow, the sound of your saliva. A soundproof room is an anechoic room, a room where there's no reverberation at all. Nada, nix, okay? None. Those are very expensive rooms. When we test hearing, we don't use soundproof rooms. We use sound-treated rooms. Read with me right here. Sound-treated rooms. Hearing is often tested in semi-soundproof rooms because soundproof rooms aren't necessary. Sound-treated rooms are isolated from the rest of the building, and they just are meant to keep ambient noise down to a minimum. And we've got this decibels business here. We're not covering decibels until next week. You can see where it's written here, less than 40 decibels, sound pressure level, less than 20 decibels, sound pressure level. That's next week. We're not going there. Basically, sound-treated rooms are good enough to enable hearing to be tested down to a minimum. They allow hearing to be tested down to 0. That's a sound-treated room. And that's where we put people in the room and put headphones on them, and we do a hearing test. Okay, so now you know what an anechoic room is. We know what sound fields are. We know what echoes are, reverberations are, okay? And we know that we, as hearing instrument specialists, test hearing not in soundproof rooms, but sound-treated rooms that are good enough to allow the hearing to be tested down to 0 decibels, okay? Now, resonance. Check it out. We're covering resonance here. It's all good. We're moving right through perfectly. I've got another 20 minutes, and by gum, we're going to get her done. How are you today? All right. Resonance. Any object has a favorite vibrating frequency. This is its resonant frequency. And as we said earlier, vibrations in any object are affected by its mass and its stiffness. Reading with me. Mass is the amount of matter present in an object. Think about its weight. Stiffness is referred to often as elasticity, or its ability to resist being bent. To resist being bent. It's stiffness. As mass increases, resonant frequency decreases. That's why when you're sitting in your living room and the people upstairs are playing the music loud, what comes through the ceiling? The bass guitar and the drums, because the ceiling is dominated with mass. Thicker guitar strings. Dong. Thin guitar strings. Ding. Why? Because thin guitar strings have less mass. Low frequency guitar strings are thicker. They have more mass. Okay? As stiffness increases, resonant frequency increases. Think of it this way, and now I'll stop sharing here and I'll just give you a different example. Think of if I have my finger sticking out here really stiff, and I try to move my finger up and down slowly, and I'm holding it as stiff as I possibly can. I run into a bit of resistance, right? But if I hold my finger really stiff like that and go, no problem. Okay? It's the same thing with an arm outstretched. Have a friend do this. Have your arm outstretched and hold it as stiff as you can, and have someone take your fingers and push them up and down slowly. You'll run into some resistance. Hold the fingertips of that stiff, outstretched arm and jiggle it quickly. The person has no resistance at all. It's just no problem. Mass resonates with lows. Stiffness resonates with highs. You'll always run into this. And guess what? You're going to run into this in your anatomy class too. Guess what the resonance is? You have your middle ear bones have a certain resonance. Your outer ear canal has a certain resonance. And we're going to finish today talking about the resonance of your outer ear canal. And we're going to finish today talking about why your ear has that shape. It has a shape to give it a specific mass and stiffness. And guess what it resonates with? The high-pitched consonants, the high frequencies of speech. We were meant to hear speech. That's the way God created us, or that's the way we evolved. I don't care. It doesn't matter. The point is the ear was made for speech. Speech and hearing are married. Okay? So we're going to talk about you need to reunite this in your acoustics as well as with your anatomy class. And Beth Fernandez, I'm sure, is going to be covering that in your anatomy course as well. But your middle ear bones, they have a resonance. They resonate with 2,000 hertz. And your cochlea, your inner ear, it has resonances too. At the entrance to the cochlea resonates with high pitches. It's very stiff. The tip of the cochlea has more mass, less stiffness, so it resonates with low frequencies. And so like keys on a piano, your cochlea is arranged in frequencies as you go around the coils. So it's really this whole concept of mass and stiffness plays its all way through the whole field. All right. Now, right in the dead center of your page, I will share the screen here, and we'll go to the very center of the page. We've looked at resonance, but now look at what it says here. Quarter wave resonator. Quarter wave resonators are mentioned often in this field. For example, the outer ear canal. Now, your outer ear canal, how long is it? It's about an inch. And we said that most science throughout the world doesn't deal in inches. It deals in metric, centimeters. So how many centimeters? How big is a centimeter? The width of your fingernail. Okay, if I can hold, that's about a centimeter. Just think about that. That's about how many of those in an inch? About 2.5, something like that, about 2.5 centimeters. I think in broad terms, sort of, kind of, you know. At any rate, look what it says here. A tube closed at one end resonates when it's best when it's 1/4 the length of the sound wave. In English, a quarter wave resonator is like this cup. It's open at one end and it's closed at the other end, right? That's what a cup is. Objects like cylinders, that are cylinders like this cup, okay, that are open at one end, closed at the other end, are called quarter wave resonators. And your ear canal is no exception. And I'll stop sharing here to show you again more closely. This is a quarter wave resonator. It's a cup. Now, I'm not going to turn it all the way because it's still got coffee in it. Knowing me, I'll spill it on my computer keyboard, so I'm not going to do that, okay? Anyway, your ear canal is just like that. It's a cylinder, and it's open at one end, and it's closed at the other end. The other end where it's closed is your eardrum. Where it's open is where you stick your Q-tip. Don't do that, okay? Anyway, so quarter wave resonators. Objects like a cup that are open at one end and closed at the other, they resonate best when they are 1/4 the length of the sound wave. So if the sound wave goes across this my whole screen here, what you can see, if you got a sound wave like that, a quarter wave resonator resonates best when it's at 1/4 the length of the sound wave. Just read with me. Now we're going to just explain something here. I'll stop sharing, okay, or I'll start sharing screen again, and we'll look at the words here. And I'll just get to where we are in the PowerPoint too. Let's just find, oh yeah, there we are. Okay, you are here. Quarter wave resonators are mentioned often in our field, the outer ear canal. A tube closed at one end resonates best when it's 1/4 the length of a sound wave. What is our ear canal gonna do? Well, let's figure it out. As a quarter wave resonator, what is our ear canal gonna resonate best? What frequency is it gonna resonate best with? Well, let's do some math here. Wavelength over the speed, wavelength over 1 equals speed of sound over the frequency. Let's kind of figure this out here. The resonance of the outer ear canal. What frequency is it going to be? So I'm going to show you this picture here. Okay, stop share. And I'm going to hold this up to where we talked about it again. Here we go. And you will see, where's it? Wavelength over 1 is equal to 340 meters per second over the frequency. We did that one already, right? What's the wavelength? That's the speed of sound divided by frequency. Now look right below it. Look right below it where it says Hz, frequency over 1 is equal to speed of sound over the wavelength. And then I drew some numbers beside it too. I said 2 over 1 is like 10 over 5. Or below, 5 over 1 is like 10 over 2. We've seen this before. All I'm doing is flipping things around here, okay? So you can figure out what the wavelength is, or you can figure out what the frequency is. And in this case, we want to figure out what the frequency is. What is the resonant frequency of your ear canal? That's our question. What's the resonant frequency of our ear canal? And we know that the ear canal is a quarter wave resonator. So we're going to do the bottom one. Frequency over 1 is equal to speed of sound over the wavelength. Well, a quarter wave resonator resonates best when it's 1/4 the length of the sound wave. So we're going to do frequency over 1 is equal to 340 meters per second divided by the wavelength. Well, your ear canal is 2.5 centimeters long. What sound wave is it going to resonate best with? One that's 4 times as long. 4 times 2.5 is 10. right? Your ear canal is 2.5 centimeters. It's going to resonate with a sound wave that's 4 times as long because it's a quarter wave resonator. So 2.5 times 4 is 10 centimeters. So 340 meters per second divided by 10 centimeters. Well, we got to make things in a fraction. They got to talk apples to apples, don't they? We can't go apples to oranges. It's got to go apples to apples. So what's 10 centimeters in English? It's 0.1 meters. So the frequency over 1 is going to be equal to the speed of sound, 340, divided by 0.1 meters. That way, 340 is in meters, and the speed and the wavelength is in meters. Meters to meters, okay? You want to make the top number and the bottom number speak the same language. So let's start again. 2.5 centimeters long. What's 4 times 2.5? 10. What's 10 centimeters compared to a meter? 0.1 meter. See, that's why metric is so nice. Everything is in tens. It just works better. It's just easier. 340 divided by 0.1. Turn on the calculator. Let's see. 340 divided by 0.1 equals 3,400 hertz. Your ear canal is going to like frequencies around 3,000 hertz. It likes those frequencies. Those frequencies are its resonant frequency. So 340 divided by 0.1, around 3,400 hertz. And your ear canal, by the way, BTW, by the way, is not made out of glass and is not made out of steel. It's made out of flesh and bone. And so your ear canal is going to sort of fudge that resonance. It's going to be sort of spread out a bit. So your ear canal resonance is basically going to be between 2,000 and 4,000 hertz. Between 2 and 4,000 hertz. It's spread all in there. So your ear canal resonance, it's a quarter wave resonator. We calculated that because the ear canal is 2.5 centimeters long, or basically an inch. We could even do this in inches. What the heck? Want to try that? Let's do it in inches. Your ear canal is 1 inch long. So it's going to resonate best with a sound wave that's 4 inches long. Okay, what's the speed of sound? 1,130 feet per second, right? So 1,130 feet per second divided by a sound wave that's 4 inches. Now, once again, you got feet on the top and you got inches on the bottom. Can't have that. You've got to have inches over inches or feet over feet. Okay? So take your pick. Which one do you want to do? Let's do inches. So it's going to be 12 inches divided by 4 inches. And the speed of sound is going to be the wavelength of that is going to be 12 divided by 3, or 12 divided by 4 is 3. Okay? And what sound wave is going to be 3 inches long? Around 3,000 sound waves that are 2 to 4,000 hertz. So you can do it in inches as well. It doesn't matter. The principle is the principle is the principle. Okay? Now, how come when you inhale helium, have you ever seen people, or have you ever seen a helium balloon? The ones that float up? You ever breathed helium? It's hilarious. I do it all the time. My voice gets really high. Okay? And it stays like that for about a few seconds, and then later on it goes away again. Why does your voice get higher with helium? Same principle. Your throat is a cylinder. From the voice, the larynx, okay, right here, your Adam's apple, that's where it's closed, to your mouth, where it's open. And it's 17 centimeters long. From your Adam's apple to your lips is about 17 centimeters. So sound is going to resonate best in that cylinder when the wavelength is 4 times as long. What's 4 times 17 centimeters? 68. 68 centimeters. But we got to make it into meters. Okay, so 0.68 meters. Right? Right? Here, this is 17 centimeters long. It's going to resonate best with sound waves that are 4 times as long. So a sound wave that's 4 times as long is going to have a wavelength of 68 centimeters, which is 0.68 meters. So now get your calculator out. 340 meters per second divided by 0.68. 340 divided by 0.68 equals 500. Your throat is going to naturally vibrate with 500 hertz. We just figured it out. Same principle. It's a quarter wave resonator. Your ear canal, quarter wave resonator. So why does your helium make your voice get higher? Read with me. Middle of page 4 or middle of page 5. Recall wavelength, frequency, and speed of sound formulas. Okay, in helium, sound goes 927 meters per second. Share screen, Ted. Show in the notes. Share screen. Go to the notes. Helium. In helium, right here, sound goes 927 meters per second. Well, 927 meters per second divided by 0.68 is 1,362 hertz. Instead of 500 hertz, now the resonating frequency of your throat is now 1,300. That's why your voice gets higher with helium. So you can answer this to your science teachers, okay? Why does your voice get higher with helium? Because your throat is a quarter wave resonator and sound goes 4 times, it resonates, it's going to resonate with sound waves that are 4 times its length, and the speed of sound is faster through helium. And because the speed of sound is faster through helium, 927 instead of 340, through 927 divided by 0.68 is 1,362 hertz instead of 500. That's why your voice gets higher with helium. Da-na-na-na-na. All right, let's finish this stuff today. The very bottom of your page. We will be talking about this again in a few weeks. We're looking at the very bottom of your page, this impedance business here, okay? All this we're talking about is now the opposite of resonance. If resonance is a smile, impedance is a frown. A frown is an upside-down smile. A smile is an upside-down frown, okay? Think of if something's offering a lot of impedance, it's like my hand going here. It doesn't want the resonance. If something is resonating, it doesn't have much impedance. Okay? They're just opposites of each other. Simple resist all objects, like this cup, like anything that carries sound. All objects offer simple resistance, like friction. Okay? Like friction. In any particular object, changing the frequency of the sound does not change the resistance. In any objects that's transmitting sound, there is some impedance, and the impedance can come partly from the resistance, as it says, resistance here, and simple resistance is like simple friction. It's equal for all frequencies in that object. And then you've got something below here where it says opposition. Opposition or reactance. Opposition is also part of impedance. So impedance is comprised of simple resistance, number 1, and opposition. Resistance in any object to the passage of sound is just like simple friction. Opposition is due to its mass and stiffness that we've already talked about. Okay? So mass and stiffness affect resonance and impedance, and so does resistance. Okay, sound goes softer as it moves through an elastic medium. Air, water, metal, all of these impede the passage of sound eventually, otherwise sound waves would go forever, and they don't. Okay, there's a time when you can't hear me because I'm too far away. Think of impedance as being the opposite of resonance, right? What it says there. An object's favorite vibrating frequency is where the least impedance occurs. And I'll finish with this slide right out of your textbooks, or this is actually in your textbook. This is in your Lass and Woodford. It's in this guy right here. It's in this textbook here that you have for this course, okay? And so you make sure you can read about all this stuff in that textbook as well, Lass and Woodford. Just look up in the index, resistance, impedance, resonance, and you'll see it right there. But look what it says here. When its opposition due to stiffness is equal to its opposition due to mass, you have resonance. That's the resonant frequency. Now, we've covered a ton of stuff, but we're done. Unit 1. You have now covered frequency, wavelength, speed of sound, resonance. Next week, we're going to delve into the decibel. We're going to look at a different dimension of sound. We're going to look at its intensity, not its frequency, not its speed of sound, not its wavelength. That's this unit. Next week is Unit 2. Make sure you print up the notes from good old Unit 2 and have your PowerPoint ready to see with me. Or you can watch it with me. You have it anyway off of Blackboard. But it's Unit 2 for next week, the decibel. And we'll cover the decibel for 2 weeks, just like we did today. I'll stop sharing screen here and ask, does anybody have questions that you want to ask me? Things that pop up to your head that are kind of, not quite sure what he's talking about. But I'll remain here for a bit. But let me know if you have any questions, in each and any one of you, okay? I'll just kind of hang around and finish the last of my cold coffee in the bottom of this here cup. So how are you doing, Lizzie? Oh, yeah, I can see you. Your mic was.
I'm good. I'm good. Sorry, I had my mute on. Just
yeah, I saw that.
Family member came in. So.
Yeah, good stuff. All righty. Well, we've had 4 of us attending today, which is great. So that always makes me feel better. And so. Feel free to write your quiz on Blackboard. Try to and there's tricks to uploading it correctly. I want to really make sure that you upload it correctly, because you want to upload it as a PDF. Okay, and I think Ms. Royer kind of went over some of that stuff during our first session, because if you upload it correctly, then I can look at it. And I can grade it, and I can make comments. Like, you can see it. You can see my comments on it. If it's not uploaded correctly, I can grade it, but then you won't know what you got right or wrong, and you won't be able to track it really properly. So it's very important that it's uploaded correctly. And there's instructions there, but as also contact Ms. Royer if you're not sure. She's excellent at this stuff. She's better at it than I am, way better. And otherwise, good old IT at OTC. They're excellent too. But just tell them, I'm in Blackboard. I want to upload my quiz correctly. I've got to upload it as a PDF. How do I do that correctly so that the instructor can make comments? Okay? But I think you may end up doing it correctly if you just go through the procedures of writing it in the Dropbox, and then just uploading it correctly. We'll see. We'll see how this all goes. Don't be surprised if you get an email from me going, gee, I can't read it. That happens. And it happens especially in the first semester, because people are just figuring all this stuff out. By the time you're in the second semester, it'll all just be easy peasy. Okay? All right.
To do it, or can we do it online? Is it something we have to print and then scan it?
No, you should be able to. You should be able to do it online.
Online, and then just upload it.
But if you scan it, I can still read it. If you scan it and upload it as a PDF, that's okay too. I can still make comments on it. Either way.
Well, it's easier for me if I can do it online because I can type better than I can write. So.
Yeah. All right. Well, yeah. For me too. If as long as it's uploaded as a PDF, we're good to go. Okay. All right. It's been a slice. Good to see all of you again.
Bye, everyone.
Hey, see you, everybody.
Bye.
I do have one question.
Oh, okay, Lizzie.
Since it's our first quiz, will we
Yeah.
be able to use our notes in our
Yes.
book?
Yes,
Okay.
you will. Yep.
I just wanted to
Actually-
make sure because I know my
actually-
other.
It's like shooting fish in a barrel. It really is. I mean, honest to Pete. If I had my druthers, you wouldn't be able to. Okay? I think you should just be able to get it. But yes, you can.
Okay.
Okay? I think your final is proctored. I think your final, you can't see anything. That's regular exam material. I'm not sure.
Yeah, and that'll be taken in the testing center, right, at OTC?
That's correct. Yeah,
Okay.
wherever anybody is. Yeah. But for you, it would be in the testing center, and for you, Kelly, it would probably be at some school.
Yeah, I already have it set up for the library here.
Yeah, there you go. There you go.
Here.
All right. It's a good one. I'll stop this one here and upload it into YouTube. It takes, you wouldn't believe how long it takes. It takes over an hour to upload it into YouTube. I just kind of have to go bye and go out and get groceries or do something. Anyway.
I lost it last week, so it's good that it's uploaded. So
good stuff. All right. We'll see you later, okay?
Okay.
All right. Bye.
Okay. Bye-bye.